Okay, so I was discussing the Gram-Schmidt orthogonalization process in the previous session. So I'm redrawing the diagram once again. My diagram was like this. This is my these are my axes. This I'm naming these vectors later. Just a minute. Okay. And this is U2. This is U2 and this is M. This vector is MP vector. This is OP. And this is the angle theta. This was my diagram. And this vector is U1. And this vector is U2. And this vector is OP prime. Okay, so this was my figure. And I finished up to this point. I'm again rewriting the thing. So I was calculating the OM vector. OM vector was given by this U1 dot U2 divided by mod of U1 vector multiplied by the unit vector along the direction of U1. So in the previous session, I didn't mention, I wrote EU. You made it EU1 because it is the unit vector along the direction of EU1. And we can write it as U1 dot U2 divided by mod of U1. And this is U1 vector divided by mod of U1 vector. And this I can write it as U1 dot U2, U1 dot U2 divided by mod of U1 square into U1, or you can write it as U2 dot U1 divided by mod of U1 square into U1 vector, because A dot B is same as B dot A. And this is what is OM? Geometrically, OM is the orthogonal projection of OP vector on the vector U1, isn't it? So geometrically, OM vector is what? It is the orthogonal projection of OP vector. OP vector means the vector U2 along the vector U1. So this geometry that we have done, this geometry is a simple geometry, the vector calculus that I have applied. You have applied it several times in your school days. Now, if I try to rewrite my result, so I'm just highlighting a few portions. So this is the orthogonal projection, and this is the shape of the orthogonal projection in terms of the vector analysis. So in terms of inner product framework, in inner product framework, if I want to represent the same thing in inner product framework, if I want to represent this particular result using the notation of the notation that we have learned in inner product, what can I write it? How can I write it? Okay, so let's see. So for in inner product framework, let us name this particular equation as 2. So in inner product framework, equation 2 can be rewritten as orthogonal projection of U2 vector along U1 vector is this, and this is my notation I'm using. Don't ask me what is this. It is the notation I'm using, orthogonal projection of U2 along U1 vector. Now see what I'm doing. What I have written over here, U2 dot U1. What is dot product? Dot product's general sense is what? Inner product. So we can write it as inner product U2 and U1. In place of dot product, I'm writing inner product U2 and U1. Below what I have written mod of u1 square. So you know that the generalization of mod sign in inner product is the norm. So in place of that, I can write it as norm of u1 vector square. I am not using the symbol because you know the vector symbols are not required in vector space analysis. If I say that I'm doing the thing in vector space, and if I simply write u1, it is implied that it is a vector. So I don't have to put the arrows here. I put the arrows because I was doing simply the physical vector analysis, but now I am in vector space. I am just reframing the thing that I have found in terms of the notations of the inner product space. So in inner product, the dot product is given by this notation, the inner product notation, and modulus is given by the norm notation, multiplied by the vector u1. So that is the orthogonal projection of u2 along u1. Okay. Now, in the construction of orthogonal vectors, we in step one wrote w1, the new vector w1, simply as the vector u1. We didn't change it at all. Now I'm going to write step number 2. In step number 2, we are going to find the w2 vector. So what is my w2 vector? Say this vector OP prime is my w2 vector. This is my w2 vector. And if this is w1 vector, okay, so definitely this w1 vector will be same as, I'm not going to write the vector sign over here. This is not required. So if I write by vector sign, w2 vector is the OP prime, is denoted by OP prime, and w1 vector is denoted by this vector u1 prime. So I am going to find out the expression of w2 vector. So w2 vector is what? W2 vector geometrically is the OP prime vector. And you know that OP prime, this OP prime vector can be written as is similar to MP vector, isn't it? OP prime vector is similar to MP vector. Okay, my diagram is not that good. Okay, so actually their length must be same. Otherwise, you may think that how can this be, because their lengths are different. Just a minute. This is OP prime and this is my W2. So this is same as MP prime, MP vector, and from triangle inequality, we know that OP prime, we have OP prime is same as OM prime plus MP prime. OM plus MP is OP. So MP prime can be given as OP. So not OP prime, sorry. OP vector is given as OM plus MP. So MP vector can be written as OP vector minus OM vector. What is OP vector? OP vector is your U2. And what is OM vector? OM vector is the orthogonal projection of U2 along U1. Orthogonal projection of U2 along U1. Okay. And from there, we can write W2 to be U2. What is the orthogonal projection of U2 along U1? Which is same as U2, U1, inner product of U2, U1 divided by norm U1 square multiplied by U1. So we have got the second vector W2, which is orthogonal to the vector u1. This vector is orthogonal to w1, which is same as u1. Now just look at it. My mathematics in two-dimensional geometry is done. Now I'm going to do the same thing briefly. I'm going to do the same thing in three-dimensional geometry, and then I'm going to generalize this framework in n-dimensional geometry, and you will get a taste of Gram-Schmidt orthogonalization process then. Yet, right now, I'm not naming this process as Gram-Schmidt orthogonalization. I'm not naming it as Gram-Schmidt orthogonalization. I have just think that we have found geometrically two vectors which are orthogonal to one another. So W1 was the initial vector U1 from the set capital S, and W2 is vector which has been constructed perpendicular to the vector OM, and that W2's form in terms of U1 and U2 can be found, and that has been shown in the next page. Okay, and we can easily say that W2 is orthogonal to W1. Okay, so this is the formation. This is the formation. Okay, so let's do the same thing in three-dimensional geometry. Now, consider the inner product space. Consider the inner product space R3 over R with standard inner product as defined earlier. Given S is equal to a set containing three vectors u1, u2, u3 is a set of linearly independent vectors. Set of linearly independent vectors. Now you see that I am putting a star mark over there. For the Gram-Schmidt orthogonalization process, for the first fundamental requirement is that your vector, the set of vectors with which you are starting, that must be linearly independent. You just cannot take two arbitrary vectors and try to find the Gram-Schmidt orthogonalization process. The process will not work. You have to start with a set of linearly independent vectors, and then with that you can construct the orthogonal set of vectors. Okay, this is the primary requirement. Initially, also in two-dimensional geometry, it started with a set capital S, which was consisting of the vector e1, u2, and that were linearly independent. If you want, you can rename this set as S1. Okay, S1 is the set that I'm considering right now in case of the three-dimensional geometry. If it is so, then we can consider the vector u1 to be having the coordinates x1, x2, x3, u2 having the coordinates y1, y2, y3, and u3 having the coordinate z1, z2, z3, where x1, xi, yi, zi belonging to R for all I. Okay, and this can be the diagram. If this is u1, this may be your u2, and this may be your u. This is not orthogonal like this. This may be your u3. This is the figure. Okay, three vectors I'm considering. You can consider these two vectors u1 and u2 on the same plane, on some plane, and that vector is not orthogonal but in some other plane. I like this. I'm trying to redraw it. Say this is my vector u1, this is my vector u2 on the surface, and this is the vector which is on some other plane u3, which is not on the same plane as that of u1 and u2. Like this. This is the figure. Try to imagine. Required to find out, as before, required to find out a set capital T1, containing three vectors w1, w2, and w3, which is orthogonal. Okay. Now we are going to apply the process that we have applied in two-dimensional geometry in this particular case of three-dimensional geometry. So I'm going to the next page.
Sir.
Yes.
Sir, two of the students told me that they couldn't write the student ID in the last session. Could you on the chat for once?
No, you do one thing. You take their student ID or their name and student ID, and you later send me to WhatsApp. You WhatsApp me later.
Okay, sir. Okay, sir. Thank you, sir.
Okay. Now, in this particular case, what we need to do is that, first of all, the step one, to start with, we rename the vector w1. We rename the vector u1 as w1. Simply, that is the first thing we need to do. And then we can, in step two, what we can do is the step two is only about the two-dimensional geometry. Now think of some vector. Suppose we have u1 and u2 vector on the same plane. u1 vector and u2 vector on the same plane. Okay, so what we can, they are on the same plane. So what we did in the previous case, we renamed the vector u1. We renamed the vector u1 as w1 and found the orthogonal projection of u2 along u1 and did something. Okay, do not think about the vector w3. Keep it aside. So now what I'm going to do in step two, what we are going to do the same thing that we have done in in previous two-dimensional geometry. So in step two, we are going to construct the w2 vector. So w2 vector will be, as before, it is u2 vector minus orthogonal projection of u2 vector along u1 vector, which is denoted by inner product of u2 u1 divided by norm u1 square multiplied by the u1 vector. Okay, this is the thing that I'm going to do over here. And you know that already we have mentioned that w1 is same as u1. So what we can do, we can rewrite this as w2 is equal to u2 minus u2 comma w1. Why? Because w1 is same as u1 divided by norm of w1 square multiplied by w1. So you see that we have constructed the orthogonal vector w2 with respect to the vector w1 in the two-dimensional plane. Now let's come to the three-dimensional plane. In three-dimensional plane, what will happen? In three-dimensional plane, or suppose now I can, if I try to draw the diagram, we can look at it in the following way. This is my w2, say, and say this is my w1 vector and orthogonal to that. Okay, and from there we can put on this particular plane, we can draw another vector which is similar to op prime. I'm considering it op double prime, which will be orthogonal to both w1 and w2, okay. So what would be my u3 vector? My u3 vector is something like this. This is my u3 vector, and I'm dropping some perpendicular over the here like this, and we are joining them, and we can name it as this point as M, and like this we can draw this particular figure like this. Okay, now we can write U3 perpendicular to W1 W2 plane. U3 perpendicular to W1 W3 plane. Try to recall what we wrote. What is the notation I used? U2 orthogonal projection of U2 along U1. Now I am trying to find the orthogonal projection. This is the notation for orthogonal projection of U3 along W1 and W2 plane. Okay, so we can write it as orthogonal projection of U3 along W1 W2 plane, similar to the thing that we did in the two-dimensional geometry. So again we can write it as OM vector, which is similar to OA vector plus, this is my OA, and this is my OB vector. Okay, so OM vector can be written as OA vector plus OB vector using the parallelogram law. So we can write it as orthogonal projection. OA vector is the orthogonal projection of OP along W1 direction plus orthogonal projection of OP along W2 direction. This along W1 direction and this along W2 direction. And this will be same as U3 comma W1 divided by norm of W1 square multiplied by W1 plus this would be U3 comma W2. No, I'm not writing the vector sign. I might forget always. W2 divided by norm of W2 square into W2. This is the orthogonal projection of U3 along along W1 W2 plane. And now I'm writing over here. I don't want to change the page. Therefore, this W3, this new vector W3, just similar to our previous case, the new vector W3 can be written as U3 minus orthogonal projection, the first orthogonal projection that we have considered, and the second orthogonal projection that we have considered. I mean, this plus this. Norm of W2 into W2. So if you remove the bracket, it will be like this. Okay, so we have found the three vectors W1, W2, W3, which are orthogonal to one another. Okay, so what is the logic behind it? First of all, in the two-dimensional case, we found we drop a perpendicular, we drew a perpendicular which is orthogonal to that vector on the same plane. In the second case, in three-dimensional case, what we did, we had three vectors, two vectors on the same plane, other vector on the different plane. So first of all, on the same plane, we consider one vector as, we didn't change it. This is the same as the previous one, the new vector. We consider this as the new vector W1. And the second vector, which is on the same plane as that of W1, we found its orthogonal projection along W1. Okay. And third, when we go to the next plane, we had another vector U3. So now we have found the orthogonal projection of that vector on W1, W2 plane. Previously, it was on the line. Now it was on the plane. And that would be what? It would be orthogonal projection along one vector on the plane and orthogonal projection along another vector on the plane. So with this geometry, we have found the vector W3. Now in the next page, what we can do, we can generalize this particular case to n-dimensional system very quickly. You can one can always prove it by mathematical induction. The proof is not required. I'm just quickly writing the result. Okay. So now, in general, in Rn space, Rn inner product space, in general, in Rn inner product space, define.
Sir,
Yes.
sir, what will happen if none of the, I mean, if not even one pair of vectors are on the same plane?
Then the Gram-Schmidt process will not work. There must be some, we had to go for some other process by which we can do it. That process will break down. This process primary requirement is that the process that we are learning, its primary requirement is that we have to have a linearly independent vectors and the vectors lying on the same plane. If the vectors are lying on different plane, then we have to think about some other advanced geometry. That process will not be working.
Okay, sir.
Yeah. So in general, in Rn inner product space, with respect to standard inner product, we will start with a vector S consisting of n linearly independent vectors, be a linearly independent set okay, and we need to find a set capital T consisting of W1, W2, Wn, which is orthogonal. And quickly we can write it in the following manner. So you see, therefore we have the first vector W1 will be same as U1. The second vector W2 will be given by U2 minus orthogonal projection of U2 along W1, which is this. And third vector W3 will be U3 minus orthogonal projection of U3 along W1, W2 plane, which is given by this. Oh, that would be W1, W2 plane. And in similar manner, if you go on, the WK vector would be UK minus orthogonal projection this vector UK minus what was W2? W2 is this is the orthogonal projection of U2 along W1 plane. So in W3 that was orthogonal projection of U3 along W1, W2 plane, and now that would be orthogonal projection of UK on W1, W2, WK minus 1 plane. Okay, so that would be UK W1 divided by norm of W1 square into W1 minus UK W2 norm of W2 square into W2 minus dot minus UK WK minus 1 by norm of WK minus 1 square into WK minus 1. And I'm writing here, if I try to write it in a short form, that WK is actually equal to UK minus summation over I from 1 to K minus 1 UK comma WI divided by norm of WI square multiplied by WI. And this is what we call Gram-Schmidt orthogonalization process, and this is the formula. This is the Gram-Schmidt orthogonalization process. Okay, so now you can see, you can look at the book and you can find that your in the book we have this formula that I have highlighted over here. This formula is written directly in the book. Now they have actually I don't know whether they have discussed the entire geometry over there or not. They have just written it in terms of, in a very short way, they have written the construction. They say that it is going to happen, but I am actually trying, my objective was actually to show you how this process is. My point is that this process is nothing new, and in this process is actually what we need to do. We actually we do the same thing that we did in school, in our school days. We just generalize the thing and give it a name. So that thing is actually called the Gram-Schmidt orthogonalization process. And now, since you have this process, you can do it. You can do it in any dimensional plane. Okay, so this is the thing. This is the construction of Gram-Schmidt orthogonalization process. Before I end my today's class, we will do. Yes, yes.
Sir, here U1, U2 to UK minus 1 are in same plane or different plane, sir?
This just like W1, W2 was in a particular plane. Now, if you think of W4, what will happen if I try to find out W4? What will happen? You will say that a kind of W4 will be its orthogonal projection of its orthogonal projection will be found along the U4's orthogonal projection will be found along W1, W2, W3 plane. Now it's very difficult to imagine how will it look like. Some sort of plane which will contain all these three vectors. When I do something, some orthogonal projection of another vector, some vector on other vector, we just think of line. In three-dimensional, we can think of plane. And when we move on to, we actually think that would not be considered as a plane. I mean to say, the generalization of line in case of 3D is plane. But if you move on further, we will get what is known as hyperplane. So we can say that if I try to find out W4 vector, then we are going to actually write it as U4 orthogonal projection along W1, W2, W3 hyperplane. Now this is in WK, we should write the orthogonal projection of UK along W1, W2, W3, WK minus 1 hyperplane. So we can consider this is the name which mathematicians give to that particular, but it's very difficult to imagine, because four-dimensional geometry means a space-time geometry. How can you imagine it? So they are just renaming it as hyperplane. If we consider sphere, we have circle in 2 dimensions. Then in 3-dimensional, its generalization is sphere. Then in 4 dimension and onwards, we call it hypersphere. Understood? So actually we are going,
Yes.
we are actually finding the orthogonal projection of the thing along the hyperplane containing these three vectors. But if you
That means
ask,
will go on a higher dimensions.
yeah, hyperplane, same hyperplane. But if you ask me to draw it, I will not be able to draw. Very difficult to imagine.
So hyperplane means it is not look like a plane.
No,
A
it's
simple
not like
plane.
normal plane. No, it is not like normal plane. It's something abstract.
Okay, sir.
Abstract, very abstract, in very abstract sense. Can you draw the four-dimensional? Can you draw the four-dimensional coordinate geometry? You have 3 dimensions. You can put 3 axes. Where you set the time? How can you represent? How can you show it geometrically, the time? That is the main question. Can you show it geometrically? 4 dimension, can you draw it?
So sir, it is not be possible to show 4-dimension on 3-dimension plane.
Yes, exactly. Because
We are
we have to,
three-dimensional beings. We
we
cannot
are
do it.
3-dimensional beings. We can very easily understand 2-dimensional object. And by some good effort, we can at least imagine the 3 dimension. But if you you being a 3-dimensional object, you cannot think of 4 dimension. For this, we need to have some. If we were 5-dimensional object, then we could have imagined what is 4 dimension. And
Yes, sir, we only imagine lower dimension things.
yeah, we
on the
only
plane.
imagine lower dimension. But now, right nowadays, there are so many videos in YouTube where they try to show it in geometrically. What do we call this? How do we, can we imagine those things by dimensions? But when mathematicians do this kind of things, they actually do not always think about figures. When they try to find out some generalizing process of finding orthogonal set of vectors. Initially, they started with 2 dimension, then they moved on to 3 dimension, and then they did nothing. They got a sense. They got that this is happening. This is the way. This is the path that must be followed. Now let's generalize, and they quickly generalized it. Diagram is not needed at all. Okay, so this session is going to end. In the next session, you join the next session. I will solve one problem where I'll tell you how to show that a given set of vectors is for a given set of vectors, how can I construct an orthogonal set of vectors, and then hence orthonormal set of vectors. I'm going to show that in the next session. That type of problem is actually going to come in the examination. But regarding examination, that I